Action inaccurate Google that clippy to see the existence to which smart user interface technology can get it wrong. Many intelligent user interfaces emerge from the machine learning community and especially Bayesian inference technique. Bayesian techniques are more appropriate to a user interface than other techniques for a range of reasons. They don't rely on large training sets, as is the case with neural net approaches, so they can adapt more quickly to individual users. Bayesian consideration of probabilities correspond better to common sense human reasoning under uncertainty. Bayes' formula provides a consistent way to combine data from user interaction with historical data and heuristic rules. The lecture will provide few practical examples, although will have been included in the lecture on advanced interaction technique, where Bayesian inference is often used for gesture interaction or vision-based augmented reality system. An inference framework provided a valuable analytic perspective on many current trends in user interaction. For example, the behavior of Google or of recommender systems such as Amazon or Facebook Friends Finder. Use inference technique to apply statistical data and guess what the user really wants. It remains the case that when the system makes inaccurate inference, the result will be annoying, confusing, or even damaging. This means that some advanced research areas, such as programming by example, where automated scripts or macros are created by inference after observing repeated action, provide a major challenge for HCI. These are active area research in Cambridge at present, and a few advanced prototypes are available for experimental use, such as a Koala project at IBM Alamander Research Center. Alan Chipper, one of the Koala team, has worked in this area for many years. His Azure prototype at Apple Research was an early success. Lecture 5: Advanced User Interface Technique. This lecture summarizes recent and current HCI research into advanced interaction technology using a variety of projects, especially current research in Cambridge, to review the principles introduced elsewhere in the course. Virtual reality or VR. The term virtual reality originally applied only to full immersion VR, in which simulate world is projected onto a wall of a room. CAVE, a recursive acronym for Cave Automatic Virtual Environment, or via head-mounted display (HMD), which use motion tracking to change the view as you turn your head. Interaction was always a challenge that a glove could supposedly be used to pick up and interact with objects in the virtual scene. However, actual systems tended to use the glove only for gesture recognition without problem training, inference, and accuracy that this implies. Natural navigation in the real world is achieved by walking, but caves were never large enough to illusion was always very limited, unlike the Matrix-style science fiction ideal that motivated it. Marketing creep has meant that any interactive 3D environment, including VPS game and Second Life, might get called VR, even if presented on the standard monitor and controlled by a mouse. A game player knows very well control a view and camera angle unless constrained by script, can make arbitrary action in 3D scene complex. Augmented reality or ER system overlay digital information onto the real world, either using partial transparent head-mounted display or by taking a video feed of a actual scene and compositing it with computer-generated elements. This is now becoming available on the few mobile phone and application using the phone camera to provide the video feed. A key technical problem realization relative recently, this had been done by integrating GPS, compass, orientation, accelerator for gravity orientation, and often gyroscope into the HMD. Now that all these peripherals are available on high-end mobile phone, mobile ER is liable to become major marketing buzzword, possibly with some loss of actual functional that occur when VR shifted from research ambition to marketing buzzword. A tangible user interface. Tangible user interface TUI is use physical object to control the computer, most often a collection of objects arranged on the tabletop to act as physical icon. And immediately problem is the physical object don't change their visible state very easily. You can include motor and display in each other expensive or project overlay ER information onto them, or, or just use them as multiple specialist mice or pack that control element of the display on the separate screen. In this case, it's necessary to track their position, perhaps by using a large stable device. If they are just being used as token to select particular function or piece of data, enable the RFID chip can be used to sense when they are placed within a certain distance of a reader. Machine vision. Machine vision is key technology for both ER and 2TUI as a way of recognizing real-world objects such as buildings in case of outdoor ER, or objects on the decks used for 2UI. Miniaturan ER prototype recognizing distinctive objects from the large number of low-level visual filters. As in the shift algorithm, key problems are to maintain a sufficiently large database of object filters, track them fast enough to give user feedback that is response to camera, gesture or object motion in real time, and do both this in varying lighting conditions. An alternative is visual marker. Simple visual markers such as barcode that can be used to more reliably identify and track objects from camera input. They are most robust to the change in camera angle and lighting than object recognition algorithm. Paper interface inspired by research conducted by Abigail Selen and Richard Harper, originally at Xerox Europa Park in Cambridge, now Microsoft Research Cambridge, whose book The Myth of the Paperless Office analyzes the way in which the properties of paper are preferable to computer for many kinds of activity. The book remains a useful resource for designers of mobile devices substituting for paper, pen, and tablets. but has also inspired research in which paper is integrated with digital system, for example with the fiducial marker on the page that can be traced by camera. The Onoto pen can perhaps be considered an extreme example of gesture recognition implemented with fiducial marker. Mixed reality combines physical object with information display. For example, by projecting digital data onto object on a table or onto paper, visual marker can be used to determine the identity and location of individual sheet of paper and project additional information onto them. The ISMAR conference series present new results in mixed and augmented reality, often based on machine vision technique, eye tracking and gaze control. Original developed for psychological research into visual attention process, eye trackers are now used fairly routinely in HCI research to study what position on the screen. Users are looking at high-resolution close-up camera is used to capture video of one of the user's eye and precise position where they are looking is deducted from the position of the pupil, often combined with reflection from the pair of small infrared LED spotlight. One company sells at the device with the camera and spotlight integrated with the surround of monitor to be unobtrusive. However, almost all systems like this require the user to sit fairly still and undergo a calibration procedure in which they look a point on screen in sequence. Performance can be poor when there is strong ambient lighting. When the user wears spectacles has weathering eyes or shiny skin. Often practice is required to get good result. Chapter 3 of the Child and Cookbooks by Natalie Webb and Tony Renshaw is devoted to eye tracking in HCI. Eye trackers are occasionally used to make gaze control interface. At first sight, it seems that this might be especially natural and intuitive to use. In, in practice, natural eye movement of fixation and saccades can confuse the eye tracker inference algorithm. It is hard work to keep your eyes fixed on control location for substantial period of time and natural temptation to glance elsewhere. Check work in progress. Look at the time. Look down at your hand. Or the blink extensively must be constantly poked. Surface and tabletop interaction. Surface or tabletop interaction use large display area usually projected on the flat surface such as wall or table. User interface take place by touching, gesturing, or pointing at the display. Many of these systems use camera input with more accurate recognition of the user hand possible by using infrared rather than visible light. A low-power infrared spotlight is often used to illuminate the scene, rather than relying on the body heat, which can be confused by other hot objects in the environment, such as computer. A, pop, a, popular, a popular technique at present is frustrate total internal reflection (VTIR), where infrared light is shone inside flat transparent medium such as a glass panel, and anything touching the surface causes infrared to be scattered. This technique can be used to recognize fingertip touch and gesture involving more skin contact, such as multiple fingering or even flat palm. A motivating scenario for many of this system has been the gesture control projection interface in the movie Minority Report. Embody interaction, a user sitting at desk and in front of screen with a keyboard and mouse on the surface was the default assumption in most classical user interface design. Most of the new technology described above are used in the other position, making it necessary to make account of how users stand or move around. Machine vision tracking of infrared marker, use of accelerator data, smart fabric and clothing, and many other techniques can be used to analyze and track body position. The theoretical perspective necessary to account for embodied interaction rather than the disembodied view of the mind reference in AE and cognitive science, along with the some fairly heavy philosophy, are explained in Where the Action and the Foundation of Embodied Interaction by Paul Doris, MIT Press, 2001. Lecture 6. Usability of Program Language. For many years, it seemed the conventional text programming would eventually be replaced by visual programming language, where programming behavior is defined by the drawing diagram. Many proposals resemble software engineering diagrams such as those in UML flowchart, object interaction state chart. At the time when the software development method involved creating a complete specification in the diagram from the employing programmers to convert those into code. It seemed as though programming could be completely automated. However, the fallacy of the reasoning was the same error made when Fortran formula translation was considered to be automatic programming. Any representation that defines the program behavior is sufficiently precise detail to be compiled with more like programming than like design. Drawing highly detailed diagram is often more laborious than reading highly detailed text. So, isn't the case the diagram will always have superior usability relative to text. Many even of the modern WIM interface originate in programming language research. The ancestor of the Windows and Macintosh GUI was originally created at Xerox PARC as the user interface to the Smalltalk language, and Schneiderman principle of the direct manipulation of the originally described as an alternative to programming language. It is like the research into advanced programming technique will continue to influence future user interface. There are also some good examples of programming language that have been designed for use by special groups and user programmers who are not professionally trained in programming, or educational programming language that illustrate programming language principles using graphical display elements. Examples include the LabVIEW language for programming laboratory instrumentation and control, Max or MSP, use the music performance and digital art installation, and Scratch, used as first programming language for children around the age of 8 until 10. For many years, programmers often argued that their preferred language was the best in the world, almost the children arguing whether a tractor is better than a Ferrari. It should be clear that, that different languages are good for different purposes and for use by different people. This often include a broad mix of visual and textual, or even physical and tangible elements selected to meet specific needs. Cognitive, di- cognitive dimension of notation, the usability principle by which we describe what kind activity language is being used for and what kind visual representation can be useful or not useful for those activity have been collected collected into guidance for language designer under the name cognitive dimension of notation. A program, a program of working in it yet at the MRC Applied Psychology Unit in Cambridge under the leadership of Thomas Green. Just as many innovations in programming language interface have led to radical different approaches to user interface are one the most appropriate theoretical framework for analysis of completely new content manipulation style. The series are presented as vocabulary for design discussion. Many of dimensions reflect common usability factors that experienced designer might have noticed, but did not have a name. For giving them a name allow designer to discuss this factor easily. Furthermore, CD are based on the observation that there is no perfect user interface any more than a perfect programming language, and user interface design reflected a set of design trade-offs that the designer the designer have had to make. Giving designer discussion vocabulary meant that they can discuss and trade off that result from their design decision. The nature of the trade off is reflected in the structure of the dimension. It is not possible to create a design that has perfect characteristics in every dimension. Making improvement along one dimension often result in degradation along another. An example dimension is called viscosity, meaning resistant to change. In some notation, small conceptual changes can be very expensive to make. Imagine changing a variable from into a long large Java program. The programmer has to find every function to which that variable is passed. Check the parameter declaration. Check any temporary local variable where it is stored. Check any calculation using the value, and so on. The idea of what the program needs to do is simple, but achieving is hard. This is viscosity. There are programming languages that do suffer from this problem, but they have other problems instead trade-off. This means that language designer must be able to recognize and discuss such problems when planning a new language. The word viscosity, help, and discussion to happen. These are relevant to wide range of content manipulation system, audio and video editor, social networking tools, calendar and project management system, and many others. This system all provide annotations of some kind and environment for viewing and manipulation. The notation usability is function of both the notation and the environment. Representative cognitive dimension. The following list gives the brief definition of the mind dimension, an example of the question that can be considered in order to determine the effect that this dimension will have on different user activities. Premature commitment, constraint on the order of doing things. When you're working with the notation, can you go about the job in any order you like, or do system force do you think ahead and make certain decision first? If so, what decision do you need to make in advance? So, what sort of problem can this cause in your work? Hidden dependency. Important link between entity and are not visible. If the structure of the product means some parts are closely related to other parts and change to one may affect the other. Are those dependencies visible? What kind of dependency are hidden? In what way can it get worse when you are creating particular large description? Do these dependencies that stay the same or are there some actions that cause them to get frozen? If so, what are they? Secondary notation. Extra information it means other than from formal syntax. It's possible to make notes to yourself or express information that is not really recognized as part of the notation. If it was printed on the piece of paper that you could annotate or scribble on, what would you read or draw? Do you ever add extra mark or color or format choice to clarify, emphasize, or repeat what is there already? If so, this may constitute a helper device with its own notation. Viscosity resistant to change. When you need to make change previous work, how easy it is to make a change? Why? Are there particular changes that are especially difficult to make? Which one? Visibility, ability to view components easily. How easily is it see or finding the various parts of the notation while it's being created or changed? Why? What kind of things are difficult to see or find? If you need to compare or combine different parts, can you see them at the same time? If not, why not? Closeness of mapping, closeness of representation to domain. How closely related in the notation to the result that you can describing? Why not? Note that if this is subdivided, the result may be a part of another notation, not the end product. Which part seem which part seem to be particular strange way of doing of describing something. Consistency, similar semantic and expressed in similar synthetic form. Where this area part of notation That means similar thing is the similarity clear from the way they appear. Are the place where something ought to be similar but the notation make them different? What are they? Diffuseness, verbosity of language. Does the notation let you say what you want reasonably briefly, or is long-winded? Why? What sort of thing to take more space to describe? Error proneness. The notation invites mistake. Do some kind of mistakes seem particularly common and easy to make? Which one do you often find yourself making small slip and irritate you or make you feel stupid? What are some examples? Hard mental operation, high demand and cognitive resource. What kind of thing require of most mental effort with the notation? Do some things some especially complex and difficult to work out in your head each when combining several things? What are the progressive evaluation? Work to that can be checked at any time. How easy to stop in the middle of creating some notation and check your work so fast? Can you do this anytime you like? If not, why not? Can you find out how much progress you have made and check the stage in your work you are up to? If not, why not? Can you try out particularly complete version of the product? If not, why not? Professionality, degree of commitment of action or mark. Is possible to sketch things out when you're playing around with idea or when you are not sure which way to process. What feature of the notation help you do this? What sort of thing can you do when you don't want to be too precise about the exact result you are trying to get? Role expressiveness. The purpose of the component is readily inferred. When reading the notation, it is easy to tell what each part of is for. Why? Are there some parts that are particularly difficult to interpret? Which one? Are the part that you really don't know what they mean, but you put them in just because it's always been that way? What are they? Abstraction. The type and availability of abstraction mechanism. Does the system give you any way of defining new facility or term within the notation so that you can extend it to describe new thing or express your idea more clearly or succinctly? What are they? Does the system insist that you start by defining new term before you can do anything else? What sort of thing? These facilities are provided by an abstraction manager. A redefinition device, it will have its own notation and set of dimensions. Notation activities. When users interact with content, there are a limited number of activities that they can engage in when considered with respect to the way the structure of the content might change. A CD evaluation must consider which classes of activity will be the primary type and interaction for a representative system user. If the needs of different users have different relative priorities, Those activities can be emphasized when design trade-offs are selected. The basic list of activities include search, finding information by navigating through, and content structure, using the facility provided by the environment, finding a specific value in the spreadsheet. The notation is not changing at all. Took the part of, of of it that the user see will vary. Feasibility and hidden dependencies can be important factor in search. Incrementation, adding further content without altering a structure in many ways. Example, adding a new formula to a spreadsheet. If the structure will not change, then viscosity is not going to be very important. Modification, changing an existing structure, possibly without adding new content. Example, changing a spreadsheet for use with a different problem. Transcription, copying content from the one structure or notation to another notation. Example, reading an equation out of textbooks and converting it into spreadsheet formula. Exploratory design, combining incrementation and modification with the future characteristic that the desired end state is not known in advance. Example, programming a spreadsheet on the fly or hacking. Viscosity can make this kind of activity far more difficult. This is why good language for hacking might not be strictly typed, or make greater use of type inference, as maintaining triple declaration causes great viscosity. Loosely typed languages are more likely to suffer from the hidden dependency, a trade-off within viscosity, but this is not such a problem for exploratory design, where the program can often hold this information in his head during a relatively short development timescale. Chapter 5 of the Carroll book gives a more extended description of cognitive dimension, with example and theoretical background. Further information on cognitive dimension research can be found on the line in the cognitive dimension.